Hello, how are y'all doing? I'm going to give you a brief review of the section 8.1 that we covered on sequences. Remember that a sequence is just a list of numbers. We put the cute little brackets around the general term, and it describes what the sequence looks like. If we think about the graph of a sequence, if this axis holds the counting numbers, and this gives us the values of A, then for each counting number, there is a value. So it's kind of like a function. It gives a value for each counting number. It's just a list of points. Here are some examples of how we can read these. Typically, we start our counter n at 1. And so if I ask you to write out the first so many terms of this sequence where the general term looks like n over n plus 1, let's first replace n with 1, and my first term would be 1 over 2. The second term, n is now 2, gives us 2 over 3. Keep going, 3 over 4, 4 over 5, 5 over 6, and so on. The next example, minus 1 to the n generates terms starting with n is equal to 1. Negative 1 to the 1 is negative 1. Negative 1 squared is 1. Negative 1 cubed is negative 1. And so this describes a sequence of values that oscillate between 1 and negative 1. The third example, cosine of 2n pi over n. The first term will look like the cosine of 2 pi over 1. Remember that the cosine of even multiples of pi is 1, and the cosine of odd multiples of pi is negative 1. The presence of the 2 means we're going to have cosine of even multiples of pi. Cosine of 2 pi is 1, and then n is 1. Now when n is 2, that's cosine of 4 pi. Now n is 3, then n is 4, and so on. So this just generates those fractions right there. A sequence converges if it has a finite limit as n goes to infinity. So if you look at the picture that I've drawn up there, those dots on our graph of our list of numbers, it kind of looks like I tried to make them tail off toward a particular number. So suppose I called that number L. If we're way out here, bigger than some very large number n, and all of these numbers live within a small distance of L, then we say that that sequence has a limit. So here's some examples. We're going to check if they converge or diverge, the sequences that we did above, I mean. Remember how to compute some of these limits. We had that tower of power for polynomial type limits, like in example 1. I have the degree on top is equal to the degree on the bottom. So as n goes to infinity, we should just end up with the ratio of the coefficients, 1 over 1. So this sequence converges to 1. And if you look at these back up here when we were making this list of numbers, doesn't it look like that those fractions are going to get closer and closer to 1? Like when n is 1,000,000, the term would look like 1,000,000 divided by 1,000,001. The second one is our example number 2 above. If I start to take limits as n goes to infinity, when n is even, I'm going to get a positive 1. When n is odd, I'm going to get a negative 1. So my sequence of values doesn't converge because if that's 1 and negative 1, sometimes the values are here, sometimes there. There's not a small interval around a number L. So this one has no limit. This limit does not exist because it oscillates. And so this sequence does not converge. All right, look at the third one. If you look at the list of numbers in number 3 above, it looks like I'm going to get smaller and smaller and smaller fractions. And we can analyze this in this way. The cosine is always going to be a number no bigger than 1, no matter what the value of n is. So if the numerator acts as a constant, no bigger than 1, and we continue to divide it by numbers larger and larger and larger, then this is kind of acting like some small number, big number, doesn't matter, it's always between 1 and -1, divided by eventually infinity. And so that limit is going to go to 0. That means this sequence converges to 0. And you can kind of see that those fractions are going to get smaller in number 3 as we listed them. Now sometimes we need to do more than use the tower of power and more than just eyeball the limit. So I've got you some examples down here. Remember, we can use L'Hopital's rule for infinity over infinity or 0 divided by 0. But if you have other indeterminate forms, we need to use some algebra first. So our other forms are 0 times infinity, infinity minus infinity, 1 to the infinity, and 0 to the, infinity or 0? I forgot. Let me look. Infinity to the 0 to the, let me go back here to L'Hopital's rule. Let's see what the other exponential form was. That's way back in section 4 or 5 of my book. You know, it's pretty entertaining to wait for me as I'm shuffling through my book. 0 to the 0 power is an indeterminate form, and so is infinity to the 0. Okay, so let's check out these. Remember, these you can use L'Hopital's rule directly, but these indeterminate forms might require some algebra here and logarithms here. In our first example, we're looking to see if this converges or diverges, so I write that as the limit as n goes to infinity of n times the sine of 1 over n. As n goes to infinity inside the parentheses, 1 over n goes to 0. Sine of 0 is 0. So the second term goes to 0, the first term goes to infinity, so it's behaving like infinity times 0. That's one of the algebra forms. And the trick here, if you remember it, is to take the polynomial term that we're multiplying by and put its reciprocal in the denominator. Dividing by 1 over n is the same as multiplying by n. But that now puts this in an indeterminate form that lets me use L'Hopital's rule. The numerator, 1 over n goes to 0, sine of 0 is 0, and then 1 over n in the denominator, as n goes to infinity, goes to 0. So here's where I can use L'Hopital's rule. I look at the limit of the derivative of the top, the derivative of the sine is the cosine, now times the derivative of what's inside the parentheses, negative 1 over n squared, and then take the derivative downstairs, get another negative 1 over n squared. Those guys will cancel for me. And now I take the limit as n goes to infinity. So as n goes to infinity, inside the parentheses, 1 over n goes to 0. Cosine of 0 is 1. So this sequence converges to 1. Ready for the next one? Hope I left enough room here. Oh, I did. That's my only example. We're going to take the limit as n goes to infinity of n plus 4 to the 1 over n. So the stuff in the parentheses is going to go to infinity. 1 over infinity goes to 0. That's one of the logarithm indeterminate forms. And the way I like to do it is I call this limit L, and then I take the natural log of both sides. The log allows me to take the exponent and put it in front as a coefficient. The way I've written it here, I have it in the indeterminate form of 1 over n, as n goes to infinity goes to 0. The log of infinity goes to infinity. So that's not quite in L'Hopital's form yet. What I'm going to do is just multiply straight across and rewrite 1 over n times the natural log of n plus 4 as the natural log of n plus 4 all over n. And now it has the form of infinity over infinity. And I can compute this limit either using L'Hopital's rule or our tower of power. Our tower of power says that a logarithm grows much more slowly than any other expression, including roots on n. So this fraction has a numerator that grows more slowly than the denominator. The limit on the left should be 0. But just for funsies, I'm going to do L'Hopital's rule. I'm going to look at the limit as n goes to infinity of the derivative of the top divided by the derivative of the bottom. That wasn't so bad. Now on top, as n goes to infinity, 1 over n plus 4 is going to go to 0. Divide that by 1, and I get 0. So one more step, if the natural log of L is equal to 0, that means our limit is equal to e to the 0, or 1. This series converges. I invite you to try some of the examples that I have on the notes that I've posted on Blackboard, and then try the ones that we have on WebWork. Catch you in Section 8 too.